Hello everyone, we are Group 21 and today we're presenting our Senior Design 2 midterm demo for the Smart RFID Poker Table. Our team consists of Electrical Engineering student Daniel Saavedra, Electrical Engineering student Matthew Miller, Computer Engineering student Diego Saavedra, and Computer Engineering student Isaac Anglero. Moving into the project overview, the system addresses the high cost of casino-grade RFID setups by providing an affordable, foldable alternative for home games. It captures hidden card data to enhance spectator engagement during live streams, while offering a dual-mode system architecture for both player training and competitive play. Finally, the hardware safely sustains long gaming sessions through integrated power and thermal monitoring.
This is the main dealer hub. It is run off of the ESP32. Here we have I2C bus that's controlled by the ESP32, as well as the LCD for the dealer hub. Over here we have the player outputs. Here's where it connects to the PDS, and this is the mode switch that we use to go from one mode to the other. These are the slots for the RFID readers for the community cards. These are the player boards, and they are all identical. Here we have another slot for the player cards. Programming pins. This is connecting to the I2C bus to connect to the main board to send the card data back to the ESP32. Here we have a UART pin, or UART pins for debugging, pin for the player LCD, and for the PCB input that connects back to the main board. This is the PN5180 RFID reader.
This is the power distribution board. It takes 12-volt input from a barrel jack. Then it passes the signal through a INA 219 current sensor that will be shown later. And it also has input ports to a 3.3 volt regulator, an MCP 9808 current, temp sensor, and a 5 volt regulator. Now moving on, here we have the INA 219 current sensor board and the MCP 9808 temp sensor board. These, like said before, plug into the power distribution board, and that will give us our power telemetry system data. These two are the regulators that will be used. That's the 3.3, that's the 5 volt. These two are using the LM2576 adjustable regulator, so they're pretty much the same board, same schematic. The only thing that changes is that little resistor R2. That value is adjusted and changed so we can get a different output from the regulator. Okay, so here's our power distribution board. If we plug it into the barrel jack that goes to the wall, we have the two status LEDs. The blue one is before the connector here that goes to the INA 219 current sensor. That's used to complete the path of the rest of the board. And if we measure here across this diode, we can see that we have the 12 volt input. Then we can connect our regulators on the board just like this. They all have status LEDs to indicate that they're getting power at the input and at the output. And if we measure the voltage of the 3.3 regulator there, we can see it's exactly 3.3. And if we plug in the 5 volt regulator, just like we did at 3.3, we have the status LEDs again. If we measure from ground to the output, we can see that we get our stable 5 volts. And then this connector here at the end, we can plug in the MCP temp sensor, and there the status LED indicates that it is getting power and it's functioning well.
Now we're gonna go into the overview of the system functionality demo section.
So here we go. If we plug in the 12 volt barrel jack, as you can see, all of the peripherals are connected and all the status LEDs are turned on, both for the 3.3 and 5 volts. Right now we have the ESP flashed with the card detection code. So if we go ahead and press the reset button, we can see the LED boots up and it's ready to scan the card. Since this is connected to the second slot, this is for the turn. So if we go ahead and pick a card, we can scan it. 10 of diamonds. We can go ahead and scan another one just in case. Ace of spades.
Now that we concluded demonstrating the overall functionality demo, we'll move on to the core specifications demonstration. In the upcoming demo video, we'll be focusing on verifying at least 3 of these parameters live that are included within the table and thus are highlighted. You will see us measure the system recognition latency by tracking how fast a card dealt registers on a player LCD screen. We will also test our sensing depth with RFIDs, of course, to prove cards scan cleanly from a comfortable distance, and verify our stable power input voltage and power consumption response time directly from the DC power rail on the power distribution board.
All right, so here right now we have the same code running as before in the previous functionality section that's able to read any of the cards for the turn slot on the ESP32. This section is going to be testing the engineering specification for the pattern recognition latency. The target spec is under 3 seconds, so as you can see, we are well under that. When we place a card over the reader, it is almost instantaneous to when the card is read. So as we can see, when we go ahead and do a trial run, 0.36, we can go ahead and do it again. Very quick.
And one more time.
There we go. We can also do it again for another card. As you can see, we can keep this logically across all the cards.
So to keep things constant, we're still running the same code on the ESP32, reading the cards. So in this spec, we're going to be testing for sensing depth. Our target is to sense at least 5 centimeters. So if we set up a ruler, so we can see that from the table to the top of the RFID reader is approximately 1 centimeter. So we're targeting for the card to be read at least at the 6 centimeter mark. So if we set up our first card, we can see it's not being read. And if we bring it down, 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 there it reads and is above the 7 centimeter mark. So if we try that one more time, it's not reading yet. And if we bring it down, that's exactly the threshold where it reads. We're still above the 7 centimeter mark. And if we try a different card, just to make sure it's consistent across all the cards, there's still not reading. And at that point, it reads perfectly. So if we bring it down, that's still above the 7 centimeter mark. So that completely verifies that this reader will be able to read over 5 centimeters and guarantee us to read through some material of the table. All right, so I just flashed on the code on our ESP32 to test the power telemetry update time. Now we can see that we are getting all the telemetry. Here we have bus voltage, shunt voltage, the load voltage, the current draw, and the power that the system's consuming, and the temperature of the main board, since the temperature sensor is connected to the main board. Also, the current being sensed is on the 12-volt line in the middle of the power distribution system board. And this will be our total current draw of our system, because that's the rail that goes into both of our regulators. And The target spec is to be under 3 seconds, and here we can see that it's refreshing quickly. Right now, we have it on the code set to 2 seconds, so we don't overload the code with data, since our specs are not going to change too much, as we can see from 1 second to the other. This can be quicker. We can also make it slower depending on what we want, but uh, 2 seconds is a good benchmark to see if we're getting any overcurrent in anywhere in our system, so we can safely shut off. And it's quick enough that we can get all of our data.
Now that we concluded the specifications demo section, this slide outlines our multi-run lab results. As you can see, our three main highlighted parameters stayed well within our expected performance thresholds across all test runs, with no major data outliers present, proven by the standard deviation. We also got to see through this test that our power input voltage maintained a stable mean of 12.27 volts, which is safely within our regulator tolerances. Finally, our physical tabletop board weight comes in around 29.6 pounds, comfortably beating our 40-pound requirement. We will demonstrate this physical architecture and its folding mechanism live in the next section of the demo. Moving to our tabletop fabrication and assembly, this slide outlines the steps for our physical layout. That started with assigning the PCB's enclosures all the way to the folding framework that you will see in the next video. Looking ahead, our immediate next steps are to fully integrate the entire physical structure with our custom PCBs that are already tested and validated against our specifications.
One of the biggest goals was making this table lightweight and portable. We did this by using lightweight wood and center hinges in the middle to allow the table to fold completely in half at 29.6 pounds. This allows somebody to easily transport and set this up on any flat surface by a single person. Additionally, we have these 3D printed component enclosures that drop into each of the slots on the table. This protects the internal circuitry and RFID hardware, making storage and deployment incredibly fast and simple.
Next, we will transition into the software section of the demo video.
This is the software overview. For the ESP32, we're programming in the Arduino IDE using the Arduino language. This is the code that was run on the functionality test that was able to read the cards. If we scroll down, you can see the tags are decoded for the cards. Similarly, if we look at the code for the MSP430, it is very similar as they're trying to accomplish the same goals. This code is still in development right now. As far as overview for the software protocols, we're using various protocols including I2C, SPI, and UART for debugging.
To conclude with the demo video, we will briefly cover the website demonstration for our project.
This is the streaming website for the table itself. Here's where we're going to show what's going on the actual table. Here we use React for the user interface, Vite to do the build and developer tools, Tailwind for all the styling stuff, and we are connecting everything to a MongoDB backend so we can store all the card data sent by the ESP32, which is going to connect through an API that we're building to send all the information. And it's also going to have information about the player uh, pots, table pots, player stack, and all that information. So here's the start page. So if we enter here, it has player 1, player 2, player 3, player 4 as a default. You can create a game session. This brings you to the dealer controls, and here it automatically sets the blinds and adds them to the pot. And here, all the betting controls on the right, all the player information, and the community cards in the middle. This is not connected to the ESP32 yet. That's still a work in progress to get the card data. And this is what it looks from the spectator mode. Here we can see on the bottom of the screen, spectator mode read only. It shows the session code that you can copy and the amount of people watching, and you can see all the player information and the community cards, the pot that is currently in play, and all those cool details.